What's up, everyone? Welcome back to Better Biomed. Folks, today's going to be the first video in a series, and we're going to base these on more professional type topics, more advanced. And I've done plenty of them on beginner type topics for some technicians, but now let's talk about advanced stuff, like advanced troubleshooting. And this one here, we are going to talk about ground, the importance of ground specifically, and this one here, it's good for everybody to learn, but if you're a senior level biomed, this is all stuff that you should definitely know, okay? Ground is the most important thing out there for everything. And if it wasn't for ground, you wouldn't have wall power. You would not have AC. If it wasn't for ground, you technically wouldn't have DC, okay? So let's think about that, all right? So let's go ahead and let's get into it. This is the first video in a series, Advanced Biomed, the importance of ground. All right, folks. So we're going to kick this one off and we're going to talk about 120 volts, okay? So in American power systems, we have something called the split phase, whereas we have the line coming in, and then we have a secondary, which is tapped in the middle to ground. And that means that each leg, 120 volts here and 120 volts here, each leg is referenced to ground. And that means that wall power AC, it's actually quite lethal for you and I, because you and I are at ground potential. And the 120 volts is actually just a difference of potential. That's all it is. So the potential, the top of the sine wave, the bottom of the sine wave, 120 volts, okay? So that's a rough schematic of what it looks like when it comes into a house. You have one side of your 120 that's going to be on one side of the bus. Then you're going to have another circuit of 120, and they're going to be 180 degrees out of phase with one another. And in doing so, you have 240 volts. And unlike Europe and all those other places that have the wonderful 200 and some volts, we have to have two phases put together, and they're just 180 degrees out of phase. And you can actually see that right here in the pictogram. You can see this one here is 180 degrees out of phase with this one, and the difference of potential. So you got two waves that are doing this. The difference of potential is going to be RMS 240 volts, okay? So you have to understand that it's based off of ground, right? So in a 120 volt system, we have neutral, which is in the circuit breaker box bonded to ground. Okay, so neutral is technically at the same potential as ground. It's just ground is not supposed to be a current carrying conductor. And neutral is a current carrying conductor, right? And you can see that kind of right here, roughly in this little breakdown. So you can see that here's our ground coming in from the pole. So your house is tapped off at the same potential as ground on the pole. You can see here, this would be the stake on the outside of your house, or you would have, even in a commercial property like a hospital, you'll have a very large ground point or multiple. And here's the neutral bar. Notice it's attached, okay? So neutral and ground are always going to be at the same potential. So ordinarily, unless you're on isolated power, you should be able to go up to the large blade and the ground blade, measure across those, and you should have around about 0 volts. Now you're never going to have 0 volts, and that is because anytime you have a conductor, I could even have a coil of wire sitting right here. Anytime you have a conductor, there's electromagnetic spectrum everywhere. Even my cell phone right here, being near that conductor, is going to create currents in that conductor, and currents equal a potential of voltage from one end of the conductor to the next, and you start having electricity. And even a wire that's sitting outside, can react with things like the sun, and a large coil of wire can have and it probably will have a potential difference between one end and the other. And that also means that it can act like an antenna. And one of the main reasons that we also have ground, especially in hospital systems, and we have redundant grounds, is because that allows us to get rid of noise. Right? All electricity, since it's based on being referenced to ground, all electricity, even noise on an electrical wire, wants to go to ground. So that's why you'll see redundant grounds on medical devices. Matter of fact, I have one right here. And we have ground reference points like this guy right here, which is also a redundant ground, because there are clips that you can put on there and they will connect to old school redundant ground panels. So you'll have a panel on the wall full of ground points where you have these large, almost like phonograph type plugs. It plugs in there, and it used to be back in the day, we used to have to measure those and measure the floor to make sure that it was not conducting and whatnot, because everything should go to ground. So even here, you'll see that we have the ground on the receptacles, and that ground is also used to get rid of noise on a lot of devices, especially devices that have AC motors. AC motors and heating elements and power supplies like DC power supplies, all those kind of components create noise, and it's everywhere. There's so much noise, it's higher than the frequency, average 20 kilohertz that you and I have. We can't hear it. It's way up there in the spectrum. We can't hear it. However, devices, if they're poorly designed, can be affected by ground or by noise. So that's why many devices will have really heavy duty grounds, and that's why we have shielded cables. Okay, so this is a rough diagram of a house electrical system, and just to let you know, all the grounds go all the way back to in the control panel, and they're all bonded together. And the neutral is also bonded to the ground, and they're at the same potential. Now, as I said earlier, and I'm going to highlight this, if you have an open neutral, if you have an open ground, those conductors will be antennas, and they will start creating voltage and be an antenna for noise. So that's why we, through our electrical safeties, we verify the integrity of ground, not just for leakage currents, but because those extra conductors can and will conduct noise from everything, especially like the lights. And they will start creating an electrical current, which becomes a leakage current, right? So noise also does other tricky things. We're going to talk about that in tomorrow's video on communication between components. Today, we're just going to focus on the importance of ground because it's pretty important. All right, so that is 120 volts. Now this right here is what's going on in a power supply. And this is a linear power supply. There's different types, right? And DC power supplies, their main goal is to take AC power, way over there, and it converts it into DC power. So devices like this and devices like this, and any modern day device is going to mainly operate off DC. In fact, if you haven't, maybe I'll leave a link down in the video description where you can see my video on the generations of electronics, because there is, and once you get past Gen 1, which is all AC devices, then you start getting into DC devices. You'll see things like this linear power supply right here. Now, this is not a very efficient power supply. There's ones that are designed much better, but this gets the job done, and it's a pretty simple design. So right here, you can see we have the AC power coming in. It goes into a transformer, which is probably going to be a step-down transformer. And then it's going to go into a rectifier. And a rectifier is basically two diodes. And those diodes are going to take one half of the waveform right here, boop, boop, boop. So one diode's going to take this half, the other diode's going to take this half, and then one diode's going to take this half, and then the other one's going to take this half. This one here is a full wave bridge. A rectifier, its main job is to make direct current, which means the power is going in one direction, from this up here, which is alternating current. So the power is going this way, then it's going that way, and then it's going this way, and then it's going that way. So the current is going back and forth, okay? That is what's happening there. And in this power supply right here, often at the transformer, it will isolate mains, and now you have DC on the other side. And the importance of that is that we're eliminating a lot of the shock hazards. Remember when I said that you and I are at the same potential as ground, which means that's why you're being electrically shocked. If you poke your pencil or something into an electrical outlet, it's because you are at the same potential as ground. As I said earlier, electricity is trying to get to ground, okay? And that's why it goes right through you. But when you go through a transformer, like this guy right here, notice how the wire doesn't go from the left side to the right side. That's because this is a level of isolation. Now there are other circuits, like this right here is definitely not a medical grade power supply, right? You can tell that because they actually have the DC side tied to ground. And you can do that. It's definitely a way of getting rid of noise, as I said earlier. So we have technically 3 ground points. So one of them is going to be over here, because remember, neutral. So this is neutral, and this here is line, which is 120 volts. And down here, remember, neutral is at the same potential as ground. Okay? And then you have this one here is being grounded. And then you have this one right here is also grounded. And this type of power supply right here, it does get rid of noise, but what it does is it puts ground back into the formula, right? In a true isolated power supply, you are separating the left side from the right side. And everything after the right side doesn't touch ground again. It's not going to. And that is because you are making it so that people can be shocked, because now the voltage is being referenced to ground again, which means you and I are at ground potential again. So this here is a very simple schematic of what's going on. So this over here, this little squiggly line, that's your AC power coming in. Only AC power can go into a transformer, okay? So it has to have a wave back and forth in order to go through a transformer. Other words, it doesn't work, right? It'd be electromagnet. It wouldn't be a transformer. So it comes in over here, and a step-down transformer means it has fewer windings on the secondary side. And then over here, this is that rectifier that we talked about, bridge rectifier 1. And you can see that this one here, they have it referenced to ground. So this would be the positive side, this here would be the negative side, and that means that this right here is the negative side because they brought ground back into the formula, okay? So this might be something that you would see, well, except for having AC power coming in. This kind of bridge rectifier reference to ground, and later in the circuit, it's also referenced to ground. That's like something that you'd see in a car. Because remember, the car body is grounded to the battery, and the other components, that way there you run one positive out to a component, and it can power itself because the body of the car is ground. So that would be kind of similar to what they're doing here. And this is just a 9-volt simple power supply. Not very efficient whatsoever. This is not a medical grade power supply. And we'll talk about that in just a moment. Big difference. So this is probably the closest I can come to a diagram of what a medical power supply is. And it might be crude, but man, whoever did this, good on you, because this really gets the point across. So right here we have the line in neutral, which right here you can see that same transformer that I was talking about. And the chassis of this device, the outside of it, is going to be ground. Remember, a lot of medical devices, the metal housing, it is grounded, right? You can see that right here. We have the ground coming up, And this right here means that it is physically attached to the enclosure. And then right here, we have an AC/DC power supply. This is isolating the power from mains. So now it comes into the internal system. And then over here, look at this. They also have another DC to DC converter, which isolates it yet again. And what's interesting is there's systems inside a medical device like a computer that can create leakage and it can create noise. So by isolating it yet again, you are isolating leakage and noise all over again. And down here, you can see that we have the applied part, which touches the patient, and it is 100% safe because there is such a tiny, tiny percent chance of getting any of this leakage from this side over here to this side over here. It's really hard, okay? If the enclosure is grounded, then this cable right here would have to wear on the case or something like that, okay? So this would be like a double insulated system. It's very safe. So let's talk about why ground is probably very, very, very important. And it's not just noise, it's not just leakage. It's because we use ground as a safe way to measure things, like a switch. Now, most technicians out there think that a switch, when it closes, it brings 5 volts over or 12 volts over or whatever, but that's not how it works at all. And that's why I brought this one here so that we can go through this just a little bit and show you guys what it looks like. So imagine this guy down here says inside the IC chip, and over here we have the MCU. Those would be IC chips, like this guy right here, okay? So when you have a input coming into a chip, it's going to need pull-up resistors. What are pull-up resistors? Okay, so on both of my examples right here, you can see a resistor here and a resistor right over here, and they're both external to the chip, right? So this is showing the pin on the chip. This over here is showing what's going on inside the chip, but hey, look, it's got a resistor outside the chip. Chips can have external pull-up resistors. However, they often have internal. You don't see them, you'll never see them, but you can see their physical traits. What do I mean by that? See this wire right here with this little squiggly line? I drew that squiggly line there along with this switch to ground. So you can see that one side of my switch is always grounded, and this wire up here, if the switch isn't closed, it's just open, right? It's just a wire. And what did I say earlier happens to wires if they're just sitting out there, just floating, they're not connected to anything? They will develop a current, and they are an antenna for noise. Now, when you're looking at a chip, and let's say a chip is looking for a logic high. If I have this little switch right here open, I just said that that wire can now conduct and it can get noise, right? So let's say one spike from, let's say this light does a surge or something, and I see a spike right here. That spike is going to come down because remember, a spike is positive voltage. It might be enough, it probably would be enough to trigger over here on the IC chip as a false positive. So that would mess it up. If it's binary, it's going to mess it up with communications, but with a switch, let's say it's an emergency switch. If I have a false positive on an emergency switch or a homing switch, you could now make that device crash because it thinks that it is at the end of the line and it's going to go back this direction. Sometimes they'll count how many pulses it's going to go in this direction because it knows if I hit the limit switch, now I have to travel, 200,000 pulses to get back to my home position or to be in the middle of the table or whatever. Those stepper motors and stuff, they just count pulses. So you hit a limiting switch, maybe even a door open switch, something like that. We'll go over switches tomorrow. But Imagine the switch. If it's open, if it is logic high, that means that it's looking for a 3 volts to 5 volts, and that means that that switch is closed. But look here, the switch is not closed, it's open. So by having logic low switching, that means that ground is sitting on my switch, and I come up here and I touch this guy, and now this whole entire line right here goes to ground. Boop, this chip now sees low. Now, ground is really hard to measure because it has to be a difference of potential. So the way that we make the chip recognize that it's not being triggered is we put voltage on that pin. And you can see up here, I have VCC and a resistor, and then it comes down here. So if this is open, what you're going to see on this pin, on this chip, even on this chip right here, if I knew that there was a logic pin that had to be high, or if it's driven low, if that switch is not closed, I can take my voltmeter on it and I can put it on there. And of course, you're going to reference the ground, which we're going to talk about in a minute, on the board. And you should see, if that switch is open, you should see either 3.3 volts or 5 volts, because ground is not being brought up. What you're going to see is 5 volts is going to come across that resistor, come in here, and you're going to see that pin on that chip sit high. And when you close that switch, if it hits a limit switch, or you close the door and the door switch, now turns on the fan and whatnot, how does it know to turn on that fan on a thermal warming cabinet? On a warming cabinet, you close the door and all of a sudden it starts the fan. How does it know that? It's got switching like this, where it brings up ground and it comes over here. Now, also notice one thing. With this switch configuration, I only have one wire. We'll talk about that in a moment when I show you some circuit boards. By having common grounds and switching on the grounds, that means that we require half the wiring, because on circuit boards, you have this giant ground plane all over the board. That means chips only need one wire, because the chip just has to kind of attach to the ground plane, which is all over the board. Again, we'll talk about that in a minute. So when you have DC devices and there's supposed to be an input on a pin on a chip, if you see that pin high, it's usually because it's got negative switching, like you see here. That is called open collector, open drain. And you see down here on my second example, this is maybe a little bit better of an example because it doesn't show what the circuitry that's going on in the inside. We have ground, we have the button. So this could even be a button like on this remote. This remote has the exact same kind of setup, whereas the buttons are going to be logic grounds. So when you depress that button, it's going to close the ground, and that ground is going to go all the way back to the chip, and that pin that was sitting high is now going to go low. So these resistors right here, they're called pull-up resistors, because when that button or whatever is open, it pulls it up to that VCC, which on my one chip I put it 3.3 volts, and on my other chip, you can see right here, I put it at 5 volts. So that's what we're talking about when we talk about pull-up resistors, and they're going to be very important when you have components that have to talk to one another. And without that little resistor right there, we wouldn't be able to measure ground, because ground is nothing, right? So the chip is just looking for a change. And that is all because of ground, because of common ground. All right, so folks, now that we have that, let's go ahead and let's take a look at some physical examples of common ground, and let's continue this discussion using real examples of real boards. Let's do it. Okay, guys. So over here, I have a whole bunch of examples, and let's start out with the power supply, because I just got through telling you guys that with medical grade power supplies, they do not bring the ground over to the output, and that is a safety reason. So what I'm going to do is I put my multimeter on continuity mode, and this right here is going to be ground. Get a little pin right there. Let's move this guy out of the way. Let's bring you guys in nice and personal like. There we go. Let's bring you in. Okay, so this right here is my ground point. I'm going to place 1 meter lead there, and notice this. So that says I have a correctly grounded, enclosed power supply. Now there are open frame power supplies like this guy over here. This is an enclosed power supply. And this large cage right here, it serves multiple purposes. One purpose is to create a tunnel for cooling, because you'll usually have like active cooling, a fan that blows it through the encase. This one here acts like a Faraday cage, which means for any RF noise that's being generated by these chips here, 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 and here, it is working to get rid of that through ground. We already explained that, but here's what I really want you guys to take from this. Over here is my input, over here is my output, and I'm going to drag this along the pins, and if you hear this, that means that we have continuity between this point and that point. Get that? And then I touch the ground point in the back. So this guy has completely isolated secondaries from the primaries. This is a medical grade power supply in all respects. Really nice one, probably very expensive. This one here is also a medical grade power supply, and this one comes out of an infusion pump. It's an older one. But one of the cool things about this guy right here is I want you guys to take a look at how we isolate one side of the power supply from the other. I told you that one of the reasons that we have ground is to get rid of noise and prevent shock. The other way that we can prevent shock is by isolating through this transformer right here, the AC side from the DC side. So everything after this transformer, which you can see by this cutaway right here, this physical cut, those there are isolation cuts. So that means that this is the super dangerous side. Everything over here is the relatively safe side. Now, how about this? I said that this side over here is the DC side. And we also happen to call DC plane, the ground plane. And that is going to be, see this large copper mass that's around most of it? And then you see these tiny little wires here, 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 these traces. This giant mass is all the ground plane. It's all the negative for the DC. See that? And now, let me show you how many devices are connected to ground. I mean, there's so many of them that are going to be connected to ground. Oop. Not that one, not that one, not that one. As I said earlier, by having ground and ground level switching, that means that you're going to only need one wire. Well, guess what? Here's that one wire. Here's that one wire. Here's that one wire. By making all of this ground, you actually made it safer, because all this ground plane, it can reduce heat, it can help reduce noise, but at the same time, it makes it so that you can run fewer wires to your components. So all they're really running is going to be positives to many of these components. And these right here are all my, these aren't going to be high voltage. This one's going to be my high voltage capacitor. These are all my smoothing caps right here. And one side of these electrolytic caps is going to be connected to the ground plane, which is over here. And once you start taking notice of things like the ground plane, you're going to see that it's absolutely everywhere. So when you're taking measurements on devices, if you look for electrolytic caps, one side of it is almost definitely going to be connected to the ground plane. Also, shielding. You see that we have the shielding right here. I also have shielding right here. See that? See how they're connected? You have electrolytic caps. That's one way of finding your ground plane. See all this mass down here? All this mass is going to be ground plane, and you're going to find these components soldered to it, like this one right here. And then you can see all the devices that are also grounded. Look right here. You got some electrolytic caps I was just talking about. See that? So electrolytics, MOVs, shielding, many of these devices, half of them are going to be soldered straight to the ground plane. And like I said, the ground plane helps you eliminate heat because it gives you thermal mass. It helps you eliminate noise. You're going to see lots of shielding, especially covering delicate components. That is going to be soldered or welded straight to the ground plane. So that's another power supply. And I'll probably use this board tomorrow in my example when I'm talking about chips and how they talk to one another. This right here is a non-medical power supply. And this one here comes out of, I think, a TV. But it's a fantastic example. It's well labeled. And this guy right here also has a large ground plane. You see, you're going to have a ground plane for all your mounting screws. You can see them right here. They put these divots here, 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 here. So when you screw it down, it bites down in and it helps solidify that ground plane. And it also makes the DC bus part of the ground. So it's attaching the DC, which I said they do not do it in medical devices, not that often anyway. Over here, this is a typical motherboard. Notice, again, they're putting the screws into the case. The case is grounded to ground. So the negative on this power supply right here is grounded. So if you start getting some anomalies, take a look at some of your fasteners. So this guy here, you can see all my different ground points. And that's, again, to help eliminate noise. And tomorrow we're going to talk about communication and how ground plays even heavier into communications, because that's how devices are able to talk with one another. Because remember, in order to talk, it's bytes. And a byte is either a 1 or a 0. 0 is no voltage, usually. A 1 is usually voltage, 3 or 5 volts. So it's going to be 0, 3 or 5, 0, 3 or 5, 0, 0, 3 or 5. And how do you know what 0 is? So all those devices have to be connected on the same ground plane in order to talk to one another. And we're going to talk about that tomorrow. But folks, that's just a semi-brief video on the importance of ground. Medical devices do have a much different ground system. And the DC side of a medical device is often not grounded whatsoever. And in fact, that's why many DC devices that are medical, they have plastic cases, because they don't want the case of that device to be referenced to ground, because that's a shock hazard. So you'll see double insulated on many devices. This guy right here, it's got an external ground point. See it right there. And it does have internal ground. Man, I wish I could tear this apart for you guys to show it. But anyway, there you have it. So that's just a brief video, I guess, on ground. It's an extremely complex topic. Ground is the one thing that makes everything work. It's also nothing, but it is something, but it's nothing. So think about that next time. And when you see a whole bunch of devices that are not working, start checking the ground plane, okay? And if you start getting a lot of noise on a device, we now know that ground, its main function is not just to eliminate shock, but also to get rid of noise. So if you start seeing a lot of noise, look for open conductors, look for open grounds. When you're doing your electrical safeties, you're checking your grounds, aren't you? Now you know why. Thanks for watching, guys. I'm here to help you guys with any of your test equipment needs, whether you need a quote or you just have a question about functionality. It's no problem. Just go ahead and shoot me an email at jbarber@bcgroupinternational.com or justin@betterbiomed.com. It's my pleasure to help you.